Hello, my name is Travis Duran. I grew up on this small farm that you can see around me. And this past summer, I've been working with Dr. Cathels from Cornell University, studying how capillary barriers prevent gas flow from the shale basins to the surface. These capillary barriers are the reason why the gas has been trapped beneath the earth for millions of years. They will continue to be the reason that the gas is trapped below the earth after we hydrofracture the shale basins. Capillary barriers are created when water is sucked up into the fine pore throats of these sediment layers. These sediment layers create pressure drops across them that are additive in their nature. And today, I would like to demonstrate how these pressure drops are additive and how they prevent gas flow migration from shale basins to the Earth's surface. Today's experiment begins with an air tank, which could be seen as a shale basin with a natural gas supply. We have it connected here to a regulator system, which supplies air to a sand column. This sand column has coarse, fine, coarse, fine, coarse sand layers. To give you a better picture of these actual sands and sediments we're using, this is the fine sand. It's around 250 microns in diameter. And the coarse sand is about 1 millimeter in diameter.
The Marcellus Shale contains only gas, no water, and the gas is overpressured. It would escape except for the capillary barriers that form at the interface of each fine-grained layer near the Marcellus. Water is drawn into the fine-grained layers like ink into blotter paper, and the gas in the adjacent coarse layer presses up against the fine layer and cannot enter unless forced. Thus, small pressure drops at each fine layer add up until they contain the pressured gas in the Marcellus, as shown in the illustration. In the experiment, I will simulate the conditions that retain gas in the Marcellus. An air pressure tank represents the overpressured gas in the Marcellus. The fine layers, interspaced with coarse layers in the column, represent the strata surrounding the Marcellus. The column is first filled with water, and then gas is introduced until bubbles pop through the top of the column. The flow of gas is then stopped. Gauges will show that the pressure drop at each fine layer is maintained steadily over time.
I'll just start increasing the pressure. And as you can see here are the bubbles now flowing from the system. The top gauge is reading at 0.20. This is right above the fine sediment layer. And right below that sediment layer is 0.37 psi. That gives a 0.17 psi pressure drop across this barrier. Looking down at the next sediment layer, we have 0.36 psi right above this sediment layer, very close to the 0.37 here. There's about a 1/100th of an error between these gauges. So we have a 0.36 psi here and a 0.55 psi here, right below the fine sediment layer, or 0.54. So this is giving us about a 0.18 psi drop in this sediment layer. Over the total length of this column, we get a 2 delta P, which is the combined total of the pressure difference between this fine layer and this fine layer of sediment.
This short video shows how capillary seals have trapped overpressured gas in the Marcellus for millions of years. These same barriers will keep gas from flowing out cemented walls, and I will illustrate this in a later video. Thank you.